All right, let's have a look. So, do we have everybody here? Are we getting used to the camera requirement now? Oh, are we still camera shy? All right, let's take a look. William, Rong, what happened to Rong? There you go. Okay, so we have everybody, right? One, two, three, four. Oh, we're missing someone. Oh, okay. Let's take a roll call. I think who are we missing? Are we missing Lillian again? Oh my, oh my. Yeah, I think we have everybody else, right? Alan, Victoria, Max, Sharona, Kevin, Emily, Ron, Jessica, Ivy, William, and Helen, and Stephen. Do we have Stephen? Oh, okay. All right. Okay. Alan, we need to see the whole thing, not just half. So turn it up. Okay. So, huh? All right. We did missing Helen. Okay, Helen, turn the. According to our class manager, we need to see the whole face, not just the upper portion of your face. So, okay, so let's not worry about. Let's not wait around for Lydia. Now, obviously, let's take a look. We're missing one person. So as far as the exercise is concerned, why don't we just go around and just okay. So this is the order I got right now today. Right, we're gonna go about like Kevin, and then Ivy, and then Sharona, Emily, Victoria, Jessica, Alan, Stephen, Max, Ron, William, and Helen. So I guess it's in the order of I guess the turn on the camera, right? Hey, wait a minute, wait a minute. What happened? How come Sharona becomes number one now? Boy. Kevin, how come he keeps on jumping around for some reason? What's your number one earlier? Did I call your name first?
Yeah,
Then how did you jump all the way down to 1, 2, 3, 4, 5, 6, 7, 8, like way back? What did you do?
I think I accidentally touched on like the camera button and closed it.
Jeez. He's being sneaky, huh? 2, 3, 4, 5, 6, 7, 8, 9. And you know what? You're still number 10. My lucky number 10, right? Because I don't have to go through the order because the ones behind you is Alan and Ivy. Everybody else is still in front of you. Number 10. You can't get away with this. All right, we started out with lucky number 10. You got to go first. All right, so everybody got hold of the exercise problem, the focus problem. Yes. Silent again. So this time around, which one are we gonna go? 1, 2, 3, 4. So for the second portion, let's see, we started out on which? From number 1 to number 12, right? Am I right? Okay. All right, Kevin, why don't you go, why don't you start it out with number 2? You ready? Whenever you're ready. Kevin? Let's go. I'm sure everybody did the problems, right? That's where we were spending time at the end of the last class.
I think I accidentally skipped this one. Hold on.
Any particular reason?
Like, wait.
Okay, anyone else want to help out?
Like the order was messed up on my book.
Okay, so be that as it may, anyone else whose book is not messed up? All right, how about Sharona, since you are up next?
I got B, so the field points away from you, and then the velocity points down, so therefore the force points to the right or east.
All right, anyone else see that? You guys agree? Disagree? Yes, it's B. Okay, so let's see, right hand rule, right? So let's see what's up next. Okay, Emily, number 3.
3, I got A.
Okay, what's the reason for that?
I don't like right hand rule or
Okay.
something.
Yeah, it's not a, I mean, it's not a, not trying to trick you out. Just right hand rule, right? That's what we've been covering. That's what we've been trying to master. So just make sure you have the different directions matched up with your right hand. What does it represent, and which one is the one that's coming out of your palm? Which one is the one pointing to the finger or thumb? So on and so forth, right? So, okay. Who is up? Victoria. Number 6.
I got E.
Okay. What's the reason for that? Yeah, E is correct. But
Yeah, slope 1 has the biggest change. And then slope 2 is the second biggest change, and then slope 3 is the least change.
Okay. 1, 2, 3. All right. You need to list the particles in order of their charge magnitude, largest to smallest, right? So in this case, what do we know? The centripetal force, right? And that is provided by what? The magnetic force. So we can equate these two, right? From the previous ones way back, the centripetal force, to the magnetic force for this particular chapters, right? So what do you got? mv squared over r equal to qvb sine 90s, right? So if you simplify, you have the q equal to mv over rb, right? That is the magnitude of the charge is what? Inversely proportional to the radius r. And then, like you mentioned, the radius of the curve 1 is smaller than the curve 2, and the curve 2 is smaller than the curve 3. Therefore, you know Q1 is larger than Q2, and also Q2 is larger than Q3. Okay, are we okay with that one? Everybody see that? Okay. All right, Jessica, you up next.
I wasn't sure how to do
Number
A.
8.
Yeah.
All right. Anyone else want to chime in? Anyone? For number 8? No one want to step up and help?
I got D for number 8 because
Okay.
so for the particle, it should be a proton because the radius is proportional to mass. So since the proton has a greater mass than the electron, then it must have a greater radius. And then for the
Right.
direction of travel, the force should point inwards, and then the field should point away from you. So therefore, it's counterclockwise.
Okay. Does that make sense? Any questions on that? Anyone? Do you guys agree with is it Sharona? See, you guys cover your face. I don't know who is talking, who is not. Sharona just answered that, right? Do you guys agree with her reasoning? Yeah, okay. Jessica, do you have any other questions? Is that clear, explanation-wise?
Yeah.
Okay. Stephen? Max? Ron? William, stop eating. You have your chance to eat later on during the break time. You make me hungry. All right, so you guys all agree with Sharona's explanation? Okay. So because we can figure out the radius, right? And what do we know about protons and electrons? Velocity Q and B, they're the same, right? It's just proton is more what? The mass is going to be bigger. Does that make sense? And then they're going to be travel with a greater radius, right? So the centripetal force is going to point towards the center of the circle. according to the right-hand rule, the direction of the force is related to the velocity and the magnitude, right? So if we do that, we know the proton is going to travel what? Counterclockwise in order for the magnetic force point towards the center of the circle. Okay. All right. Any questions on that? Okay. Let's see. In our problems, okay, the next one is 12. So who is our lucky winner? Steven, you Lex.
For 12,
Mm-hmm.
I said the answer is E.
Okay. What's the reason for that? E is correct. Yeah.
Um, I I'm not completely sure, but I think because it's north is on the from north to south is counterclockwise
Mm-hmm.
direction, and then the current is going up or like out of the page.
Okay.
And then I think that causes it, the magnetic force to go north.
Yeah. That's the only way to explain that, right? The magnetic field is always directed from North Pole to the South Pole. So if we're going to use our right-hand rule, the magnetic force, it has to point to north as well, right? The magnetic force pointing to the north. Therefore, that only going to apply to the figure 1, right? Point current is what? Out of the page, pointing towards out of the page. Okay, so again, you use your right hand rule, right? So the fingers out of the page, that would coincide with that. All right, let's see, what else? Okay, now where are we right now? So we have Steven. So whoever, hey, what happened to Emily? Why you jump down to you're doing the same trick as Kevin? Jeez, come on. So remember who is up next? Max, Ron, William, Helen, Ivy, and Alan, right? And Kevin as well. Kevin is going to be going after Alan. We can skip Emily for now, unless you want to do it again, right? So the purpose for you to turn off the camera is unless you wanted the second participation point, right? So we're okay with that, you know. So okay, anyway, let's go back to our PPT again. Everybody has a copy of that? So it's really up to you guys to see, you know, whether you're going to go with the PPT or you wanted to stick with the textbook, because the textbook might give you a little bit more detailed explanation regarding the formula change, or say deriving how the formula is derived from. All right, so let me change. Yeah, go ahead, Alan. Let's see. speaker view. No, that's not what I want. All right, I'm going to minimize our picture so that everybody is going to be on the same page. Now, I think last time we stopped at section 6, right? So for the remaining slides, we're talking about section 6, the torque on a current carrying coil, because the current is going to be different direction coming out of that particular coil, right? It's also folded on, could be a whole bunch of different turns of metal coil. So when you put it into a magnetic field, right-hand rule is going to predict the 2 different direction of wire is going to causing the coil to move in such a direction that if they on 2 different ends of the coil, they're going to be moving towards different direction, meaning the magnetic force is going to make sure the coil is going to rotate. And also, the loop tends to rotate such that the normal becomes aligned, all right? Meaning it used to be independent, perpendicular. Then the normal would be lined up in the same direction as the magnetic force. Okay, that's what's causing the coil to rotate. So if you wanted to calculate the torque, we can do this according to the graph, right? Everybody on page 27. You know what? Let me just share a slide with you guys. So this way everybody is going to be on the same page. Okay, everyone see that? Okay. So the loop is going to tend to rotate such that normal becomes aligned with the magnetic field, right? Pointing to the same direction. And you can start it out in this, but because this end and this end, they're going to experience a different direction, opposite direction of the magnetic force, that it's going to make them rotate, that the particular coil is going to rotate. And then it would line up with the magnetic field. Okay, the end result of this being rotating this side and this side going here, causing this going to line up normal direction in the same direction as the magnetic field. All right, so, and this is the formula to calculate what is the total net torque, because you have 2 opposite direction of this, right? And also you will be able to figure out this end, and what is the total area. And then by our definition, this is going to be calling magnetic moment, N times I. A is the area, right? And B is the magnetic force. Theta is the angle. Okay, so are we okay with this from here to here? Everybody see that? Because you have 2 of the same term, right? So you add it up and cancel the 2. And then L times W now would give you the area. Okay. Given the example, remember we have n number of terms, right? So if they give you the 100 turns, we need to figure out each turn is what, and then times the 100, right? Because there are 100 loops lumped up together. This is the wire area. This is how many turns. And then what is the current? So if we go back to this particular formula, right? This is going to give us the net torque, right? This is the formula for that. So given this current and the area, we should be able to figure out what is the magnetic moment. And once we figure that out, we should be able to figure out maximum torque. That's when the angle is what? When we have 90 degrees, right? When it's perpendicular, that's when we have the maximum torque. Okay, everybody see that? See how we got the magnetic moment in terms of the formula? Oh, wait, going too fast. Okay, so this is our definition of magnetic moment. And then that would give us this particular, oh, wait, hold up. So I guess this term should cover NIA altogether, okay? And then times B times sine theta. I just want to point out for the magnetic moment wise, okay? So be careful with that. So this is how we derive from the magnetic moment, and then times B times sine theta. Okay, everybody clear on that? No problem with this? Okay. And also we talk about the torque on a current carrying coil. Similar approach, different orientation, right? Which way is rotating, as well as say, you got two different currents coming in, and therefore that's going to cause in this to rotate in that particular magnetic field, right? And also we have a right-hand rule number 2, okay, making sure which one points in what, which direction is represent what, right? So in this case, we need to point the thumb of the current direction. Tips of the finger would be the direction of the magnetic field, right? Remember, it's going to be a half circle, right? That's what they say. Curve your finger, curve your right hand into the shape of a half circle. And then whatever the fingers are pointing towards, that would be the direction of the magnetic force. Okay, are we okay with that? So again, right, how are we going to calculate the magnetic force? In this case, we have another constant that's called permissibility of free space, right? That's going to be represented as such. Make sure we got the unit correct, right? Tesla times meter over amp. Okay. All right, example. We got this long wire, carries this much current. Particle has a charge of this, is moving parallel to the wire with such a distance. So once we know the distance, what do we know? Anyone? We also know the speed of the particle, right? So given that distance, that would give us this, the radius, right? So the magnetic field produced by the current is given as such, and then we need to re-represent B as here, right? That's going to associate it with this particular constant with the current as well as 2 pi r. So in this case, given the current, we know that particular material, we should be able to figure this out. Okay, so hold on. Okay, so in this case, we can figure out this. We should be able to figure out the force, right? If we go back one more step, right? Do we know the current? Yes. Do we know the charge? Yes. Radius, speed, then we should be able to figure out the magnetic force, right? And also, how we're going to figure it out direction-wise? Right-hand rule. Second right-hand rule. Okay? We know the charge, we know the speed, know the constants. We know this, we know that, and then we should be able to figure this out. Okay. Questions on that? And also, because the current on the wire, they would exert forces on each other, right? And we know if we go in this direction, you would be, the forces is going to be pulling one way and going the other way by using right-hand rule. But if the current is going this way, these two forces actually is attract. Right? If we go opposite direction, we know it's going to be repelled. Same thing. It's produced by the right-hand rule. We know the direction of that magnetic force created by that current. Use right-hand rule, we can figure that out, right? So these are the real application, or say a simple solution when given various factor, right? Right-hand rule, you need 3 variables. Given 2, you should be able to figure out what is the third in terms of the direction wise. Okay. Now, obviously, you got to twist your hand a little bit, but right-hand rule is the only way to go when we deal with the 3 different, force, magnetic field, as well as the current. Okay, net force on the coil, right? We did this one already. If they given different direction wise, that's going to cause this to rotate, and in such a way that normal is going to be lined up with the magnetic force, right? And if we have a loop of wire, this is what we're going to have, and they call it center of circular loop, right? Again, right-hand rule, right? Remember the direction. So if we have some kind of charge and going through like this, this is exactly the kind of magnetic fields produced by this particular circuit, right? Going in the current like that, right? So if you actually see this, right, that's going to be your right-hand rule. Your fingers is actually going through what, right? If you're going through that circle, that would be the current direction. Okay, so making sure we use our right-hand side, and then we'll be able to figure it out. The magnetic force is going to be half circle, remember, right? So that would be going out of your palm towards that. Net magnetic field, given this formula, we should be able to figure it out. Now, again, right, this is where we're going to derive from. Now, obviously, in this particular case, you have 2 magnetic field, right? Do we see that? One is caused by this particular long wire, and then you're going to have a circular loop that also has a current too, right, with the radius of such. Okay, so for this particular, let's say at the center of the loop, what is going to be the magnetic field? Now, obviously, at this point, is going to be caused by this wire as well as this wire, right? You have 2 different current that's going to be going on, right? That's going to be exert forces on that particular point. And then, for you to calculate that, the first one is this, second one is that, and then we should be able to figure it out. Let's see, which one is this? This current is going to be bigger than I2, right? If I remember correctly, one is A, the other one is what? 2, yeah. Any questions on this one?
Why are you subtracting it?
Okay. What's the direction for this? Using right-hand rule, right? We can figure it out, right? Because these two currents are going in opposite direction. Does that make sense?
Yeah.
This particular particle influenced by the I2 versus I1. All right, if you use right-hand rule, the direction of the magnetic fields are opposite to each other. Therefore, you gotta find the net magnetic force produced on that particular center by these two different currents. All right, when they go circular, what does that mean? That means I2 is going to go in here and then actually point upwards on that particular point, right? Closest to the loop I1. Right? Does that make sense? So it has to be offsetted by, if this current is actually smaller than this one, then we would use this minus that. But the caveat is, whether it's bigger or smaller than, you have to use the right direction, right? In this case, using the right-hand law, we know the B1 is pointing towards this direction, B2 is pointing towards this direction. So whether it's going to be B1 minus B2 or B2 minus B1, that's going to be up to which current has a bigger value. Does that make sense? Yes? No?
Yeah.
Still not totally so? Right? We need to figure out on that particular point, what is the magnetic field causing by current 1, and what is the magnetic field point causing by I2, direction-wise, right? And then what you need to figure out is, all right, do we have I1 bigger than I2? And that would give you, say, which field is bigger, right? What is the net magnetic field? Okay. Yes, no? Still have any questions? Still not clear? All right. Refer to the chapter 7, not chapter 7, the section 7. When they going through the formulas, they probably have a little bit more detailed explanation in the textbook. Okay. So for section 7, they should be able to show you the. Let me see. Oh, okay. Well, we're not sharing screen right now, but I can double check. Yeah. So take a look at the example number 10. They will show you how they derive this particular formula. Okay. And they tell you which one is bigger, right? You have two different opposite direction of magnetic force. So if B2 is bigger than B1, we actually use that, the second term in front, and minus the first term. Okay. All right. So take a look at the example number 10 on that. I wanted to say section 7. Yeah, on the section 7. So they will explain this particular problem in more detail. Solenoid, you just say, let me go back to the, uh-oh. What are you guys seeing right now? Can you guys see the PPT?
Yes.
Go back, okay. Magnetic fields caused by current, yeah, attraction, repulsion. Again, right-hand rule, right? That dictates this. Opposite attracts and similar repel. And for the solenoid, this is going to be the formula that would represent the magnetic field. So we can simplify that a little bit. Number of turns per unit length. Okay, that's the N. How many turns that we're going to have in there. And these are the, I guess, real application, right? In the TV, this is what we got. And we have Ampere's law for static magnetic field. So that would give us that particular formula. It's called net current passing through, bounded by that particular surface. Again, highly recommend that we check it out, section 8 for the formula derivation, right? How we derive from here to here using the integration, right? So a little bit of calculus involved here. So magnetic materials, certain materials that we can use to do this permanent magnet, right? And so on and so forth. Real life example, a speaker, you know, how is that going to be amplified through here, input, output? So some interesting reading. Also, you know, electromagnetic trains, right? How is that going to work? So that's the last one. Like I said, take a look, section 7 and 8 for a little bit more specific explanation. And yeah, what else? What else? All right, our class manager is still explaining the order that's going to be showing up on top. All right, well, I guess the rule of the thumb is don't, unless you have an excuse, don't turn your camera off. You know, otherwise it would have messed up the order. So, okay, well, let's see, what else? We have this being covered, and let's see, I'm gonna figure out what are we gonna do once we finish chapter 21. If I remember correctly, let me take a look. We're gonna do chapter 22, magnetics. Actually, after chapter 21, we should do a quiz. That's going to be cover, what is this, 18, 20, 21, 3 chapters. Okay, yeah. Now, typically, we kind of coincide with the kind of lab in between, right? Is that how it's used to be doing? The previous instructors, whatever the labs and, you know, in between, those are the chapters that you guys should do. You guys do a quiz on it, right? Am I right? Is that typically how it goes before? How many tests have you guys did? How many have you guys done so far?
We did 3 tests and 3 labs.
3 tests so far. Okay. And any retake on the test? All non-necessary?
I think there were retakes, but I don't know about them.
Okay. So I assume you did pretty well on the test, then you don't need to retake, right? Okay. All right. So, like I said, we're gonna cover this coming up on Thursday, and it's gonna be focused on 18, 20, and 21. Okay. So my advice is definitely do some review on those chapter reviews, chapter summaries. Highlight the chapters or highlight the sections that we have covered so far. 1, 2, 3, yeah, this one, and 21. I think if we use the time allowed accordingly and don't worry about the lab so much, we should be able to cover the rest of the material till like what, chapter 31. I think that's the last one we need to do. Yeah. Okay. All right. Let's see. It's gonna be 21, 23. Okay. All right. Any question on that? All right. You guys can take a 10-minute break, and we come back, and they're gonna be work on the remaining problems from chapter 21. All right. So 10-minute break. We come back at 7. All right, do we have everybody back? William is still eating. Don't want to see us. All right. Steven? Okay. Max? Okay. Now, for some reason, we only have the abbreviated set of problems, right? When we deal with the focus problems in, especially textbook and let me see. We don't have to open this. Give me 1 second. Give me 1 second. Okay, so if we go through the summary, the concept summary, like I mentioned, some of the formula, how they derived, and also how we're going to do the calculation. So even for section 10, those formula summation is the formula summary is going to be critical. It's going to be very, very handy, right? Comes in handy, important. If you go through the concept summaries as far as the 1, 2, 3, the different sections is concerned, we can take a closer look at some of these, like Ampere's law, the magnetic materials, and so on and so forth, before we dive into the specific problems. Now, again, we don't have everything here that we need to do, so we only have a few. Yeah, 1, 2, okay. Yeah, we only have a few here. So so we have what, 13, 16, and 17. And that's it. So let's take a look at those. Yeah, looks like we might be able to finish early today. Okay, so is everybody on it? Page 668. All right, so we only have 3 that we need to work on. 13, 16, and 17. Okay, so let's spend what, at most 10 minutes. We should be able to get this done, right? 3 problems. Let me know when you're done, right? You can text me. Let me know when you finish. Okay, so let's go. How are we doing on time? Are we pretty much done? I only see one reply from you guys. Everyone else is still working on it? You done, Jessica? You finished room?
Yeah.
Okay. How about everybody else? If you're done, text me. Let me know. Yeah. Stephen Ivy. Okay, let's see. Quite a few already said you finish. Now, okay, let's take a look. So who are the ones that haven't stepped up and did the problems? Is it William? Max, did you did it? Did you do it?
No, I didn't.
Okay.
Yeah.
So it's Max and who else? Kevin? Was it? Okay. All right, Max, you want to start it out?
Yeah.
Okay.
I think this one, number 13, is
Mhm.
C.
Okay.
Because
fine.
when the force is parallel to the wires,
Mhm.
there is no force.
Okay.
And
Why is
like
that?
when the magnetic field is parallel to the wires, there's no force.
Okay. That's right hand rule number 1, right? We can use right hand rule number 1. Okay.
And then when the magnetic field is perpendicular to the wire,
Mhm.
and since the two wires have since the two currents have different directions, so the force would be different directions too.
Mhm.
So they will cancel.
Okay. Different
So there,
direction. How
yeah,
about the magnitude?
magnitude is the same.
Okay. Right. So they
So
cancel
there,
each other. Okay.
yeah, and like, and then so there's no net force, and then there's torque.
Okay. There is torque.
Yeah.
Okay. All right. Does everybody else see that? All right. So the net force is 0, but they will exert a net torque with respect to the axis. Okay. Simply because the distance is different, right? Okay. All right. So let's see. Kevin, you're saving the best for last, right? So you can run and you can't hide.
Yep.
All right.
So for number 16, I'm slightly confused, but I think it's only one.
Okay. Number 16. So which one you pick?
I think it's only one, like use the second right-hand rule.
Mm-hmm.
And only on one that the two magnetic fields cancel out each other, I think.
Hmm. Right. So for 16, what is your answer?
C. I mean B.
16. Okay. Do you guys agree with him or disagree or any opinion at all? So Kevin choose B, right? Okay. So what do you guys think? You guys choose B as well? Same, right? Yes?
Yeah.
Some of you, yes. Some of you didn't say anything. Well, feel free to share your opinion. For problem 16.
A, 2 and 4.
So you have 2 and a 4. So what does that mean? That means it's the A? First one?
Yeah, I got A for 16.
Okay, you wanted to offer your reasoning for that?
Because for 2 and 4, according to the right-hand rule number 2, they would cancel out.
Okay. So you use right-hand rule number 2 to figure out the magnetic field, right? From the top in 2 is pointing into the screen, right? And then from the bottom is out of the screen. Therefore, the net magnetic field in 2 is 0, right? And also in 4, it's the same thing, points into this, and from the vertical wire is out of the screen. Therefore, that one, the net one is the net magnetic field is also 0. So you wind up with 2. That's 0. Okay, does that make sense? So do you guys see how come B is not correct? Anyone else?
Yeah, I got it.
You got it now? Okay. All right. So let's see. We have one more to go. Any volunteer? Anyone who hasn't done it? I thought everybody else covered, right? Who hasn't done anything? Who hasn't got a chance to do the problem today? Everybody did it? Max, did you do it?
Yeah, I did.
Okay. Are we missing somebody? Everybody did it? We didn't have that many problems today, right? Who else? Okay. All right. So who is our lucky number? Lucky number 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Oh, Ivy, you are number 10 on my screen right now. Care to help us do the last one? 17.
I wasn't really sure, but I kind of just guessed.
Okay.
I said C.
All right, you took C. All right. Let's take a look. Now we said we're going to go reverse order. So it's going to be Alan 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Jessica, you number 10, going from the reverse. What is your answer?
I put B.
You choose B. Why?
Yeah. Because like A has an attractive force on B while C has a repulsive force. So it goes up like twice. So
Okay. So B is attracted to A and repelled by C.
yeah.
Right? Therefore, you got the force that's going to be reinforce one another.
Yeah, they're in the same direction.
Correct.
So
Okay. All right. So does everybody else see that? Everybody else agree with Jessica? Still have any thoughts on that? Questions on this one? Yes? No? Well, Emily is just so tired. Wake up, Emily. You agree? Okay. All right. So do we see that? So this one should be B, right? And also because the A and C are equal distance, therefore their force got to be equal, right? For the B on A as well as B on C. Therefore, the net force on B is going to be magnitude of twice of, let's say, force F2FBA. And also the net force exerted on A is less than this because A is attracted to B, yet repelled by C. So some of this is going to be canceling each other, right? Therefore, the net force expected on Y or C is going to be less than on A when it's repelled both by A and B. Okay, so, and also because A is twice as far as B, so their force is going to be a little different, right? As we can see, the further out, it's going to be a little bit less. Okay, all right. Any questions on this one? No problems on that? Okay. All right. Let's take a look. So what do we have today? Homework. Let me make sure we got the homework. So 45, 49, 51, 57, 65, 69. Okay, do we see that? 6 problems? All right, and we're gonna be on Thursday. Let me see. I remember you guys told me typically you have the whole class is covered by tests. Is that right? Is that how you guys did it? Typically, how many problems you guys do for your tests?
25 multiple choice and 3 FRQs around.
Oh, okay. 25 multiple choice. Typically, I like to do. I don't typically like to do multiple choice. I like students to show steps and procedures and show how you reach your answer. Sometimes even if you don't get the right answer, you might still get partial credit based upon the steps. So most likely we're not gonna have any. We're not gonna do any multiple choice. So most likely it's all gonna be, like FRQs, if you wanted to put it that way. Now, obviously, based upon the right-hand rule, the introduction of that, sometimes we might do some reasonings, choose the choice A, B, C, D, E, but rest assured, you still have to show your reason, right? You still have to show how you get that particular multiple choice. Okay, so if we do have something like that, you don't want to just say, oh, it's A, that's it, end of story. We're gonna ask more than that. Okay, so all right. Again, most likely it's gonna take an hour, and we're gonna be moving on to chapter 22. But I'll be more than okay with being flexible on the time. We'll see how the test goes first. All right, see how long that's gonna take, and then we go from there. If we got enough time, then yeah, we deal with the second chapter. If we somehow everybody is taking longer, then we just make sure we finish the test first. Alrighty, okay. So I guess I will see you guys Thursday, and we're gonna start it out with the test on chapter 18, 20, and 21. All right. Okay, so you guys are free to go. I'll see you guys on Thursday.
I have a question.
Yeah, sure.
For number 16, for the second right-hand rule.
Mm-hmm.
So you point it in the way of the current, right? And then I don't understand how, like, when you curve your fingers, how you can tell the.
Hold on. Give me 1 second. Let me get the problem first. You're talking about 16, right?
Yeah.
Okay.
On the focus on concepts part, not the questions.
And which?
Is the one we just covered.
Right. Hold on. Give me 1 second. I've closed a whole bunch of this already. Okay, so they said which one of the situation give rise to a zero net magnetic force at P?
Yeah.
Okay.
Can you explain how the second right-hand rule works again?
Okay, so which one did you pick?
I picked B.
B?
Yeah.
Okay, so when you have B, when you have the current going into opposite direction, right? What is the net outcome? What is the net results?
Sorry. It's repelled.
They're going to be reinforce each other. They don't cancel each other.
Yeah.
The magnetic force and the magnetic field is not going to be, they're going to be reinforced on each other because it's the same direction. Okay, the reason that 2 is such a way is because if you use right-hand rule, these two, when you're going, they're going to be canceling the net magnetic field.
How does the second right-hand rule work again?
Well, when you use the second right-hand rule, what is going to be the half circle? What is going to be the magnetic field? The magnetic field is what? You have the current direction, right? That you can use your thumb, right?
Yeah.
the magnetic field is going to be the curl out of your finger,
I thought
half
the field,
circle.
I thought the field was flat.
Well, that's why when you curve it, you got to use your,
But this is only for wires, right?
yeah, caused by current.
Okay. So if it goes this way and I curve it like this, how do I know which way the magnetic field is? Is it like the way that my fingers curve?
So basically you have a current, right? Where is that going to go? That's going to be the thumb, right?
Yeah.
Okay. So, and then your finger, the tips of your finger will be the direction of the magnetic field. So if you take a look at the graph, right, in this case, for that particular point, where is your current going to be? Right,
what
for your
number?
number 2.
For number 2.
Oh, I mean, okay, let's just say for your number 1, right? If you choose the, B, which is 1. So when you take a look at the P, when you're facing this way, right? If you take a look at the top wire, where is that magnetic field is going to be pointing to?
The center?
Yeah, for that particular point. It's going to be into the paper, right?
Yeah.
Now, if you take a look at the bottom wire, where is that going to be?
Into the paper?
Into the paper, right? Do they cancel each other? No,
No.
they reinforce each other. Does that make sense?
But if for number 2, won't they both also be into the paper then?
Okay, so if you take a look at number 2, again, same wire, right? Going that direction. So for the top wire, where is the magnetic force going for that P point? Into the paper, right?
I don't really understand what you mean by into the paper.
Well, the magnetic field, right? What is your tip of the finger? Where is it going to go?
This way?
No, where's your thumb, right? First of all, it's always your thumb is the current direction, right?
Mm-hmm.
So if we're doing number 2, right?
Yeah.
Okay, so for the top wire, where is the magnetic field going to go at the point P?
Like this?
It's into the paper again, right?
Okay.
Just like number 1, right?
Does into the paper mean like down, or does it mean like towards me?
Into the paper.
Okay.
Away from you. Away from you for that P point.
No, what do you mean by for that P point?
Well, because you have 2 different wire, right?
Yeah.
They would have different direction, or say they could have, right? Depending on the current direction.
But don't the currents go in the same direction?
Well, for the excuse me, for the scenario number 1, do you agree using right-hand rule? It's going to be a reinforcement of each other. It's not going to be a F0.
Yeah.
Does that make sense? Right? If you use your right-hand rule, right? Let's just take a look at scenario number 1. Where is that particular P point, the magnetic field, going to go? It's into the paper, right? When you go through that P point, right? For scenario number 1, top wire. What about the bottom wire? It's into, right? Again, right? Your current is pointing to the left, right? On the bottom, right?
Mm-hmm.
Therefore, for the top wire, it's going into the paper. For the bottom wire, the magnetic field is going into the paper as well. So they don't cancel each other, right? They would add it up to each other. That's scenario number 1. If you take a look scenario number 2, again, for the top wire, you use right-hand rule. It's into the paper. Now, what about the bottom wire? You use right-hand rule. It's out of the paper. You see that?
This is like in relation to the point, right?
Correct.
I still don't see how the point relates to this.
Well, again, you have two different magnetic field. One is caused by the top wire. The other one is caused by the bottom wire.
Okay.
The reason they cancel each other is because for the first one, right? You take a look at the first one.
Yeah.
What does the top wire do?
What do you mean by that?
Where is the magnetic force going to go at the point P by wire,
So
by the top
current
wire?
goes this way. Current goes this way, and then it curves like this, and it goes down.
Well, it's not down, it's into the paper. Because it's curved, right?
Uh-huh.
That's where your fingertips is going to go. Okay, you can say it's go pointing down. That's fine. Yeah.
Okay.
What about the second? What about the bottom wire?
Well,
It's going
at the
up.
top it goes like this, and it goes down into the paper. At the
Uh-huh.
bottom, does this goes down into the paper.
No. We're talking about scenario number 1.
No, I thought we were talking about number 2.
Well, number 2 is different now,
Okay.
right? Because the bottom wire, you have a different direction of the wire.
How come? I thought it was dependent on the current.
Right. Look at the current.
Aren't they going the same way
No. Look at the current.
for number 2?
Yeah. The bottom wire is going opposite direction of scenario 1.
Yeah.
Right?
Yeah.
So when you take a look at that particular P point for the top wire, what do you got?
Wait, hold on.
You got the magnetic force pointing downwards. What about the bottom wire? For that particular point, you got the magnetic force pointing upwards, opposite direction.
Yeah, but if I do it like this, how would that be upwards?
Well, for your second, you're talking about the second
Yeah,
scenario,
the
right?
second one, I see how the top goes like this and it goes into the paper. For the bottom, isn't it just the same thing?
No, it's not. It's going in circular motion, right?
Yeah.
So if you take a look at the circular motion, it would make better sense. Because when you go through a circular motion, you can say the P point influenced by the top wire is either going into the paper or going downwards. The P point influenced by the bottom wire in scenario number 2 is actually going upwards or going out of the paper.
Like towards
Do you see
me.
that?
Right? When you say out of the paper, does that mean towards me?
Towards you, correct. The top wire is going into the paper away from you. Therefore, these two cancels out.
But you said it was a circle, so how wouldn't it go away from me and then towards me again if it loops?
No, it's not looped, right? Because you have to pay attention to that particular P point. We have different wire. So the P position, as far as related to the wire, is different, right? For the top wire, where is that P? It's underneath the wire.
Yeah.
For the bottom wire, where is that P point?
Above it?
It's above the wire, right? So when you do your right-hand rule, you have to figure it out. It's either above or down low, right? Does that make sense?
Yeah, kind of.
If it's up, when you talk about the magnetic field caused by the top wire, the P point is below the wire. Therefore, the magnetic force, you can say it's pointing downwards.
But isn't
Right?
that two-dimensional? I was thinking more three-dimensional.
Three-dimensional is the same thing. You can say it's pointing towards the paper, away from you, for that particular point. Even though as a whole, right, there is going to be another point above the wire number 1 or the top wire on top of it. That's going to be symmetric to that P point, but that's not our concern. Our concern is right at that point P. Where is that direction going to go by the top wire? And that would be into the paper. So what about the same point? That's going to be influenced by the bottom wire. That's going to be out of the paper towards you. Therefore, these two are exactly opposite, simply because the P point is different in relative position-wise to these two particular wires. P is below wire A, and then P is above the bottom wire. Below the top wire, the second case is below on top of the second the bottom wire. That's why it's caused different directions.
I don't really understand why you say above, because when I think of the bottom wire, and since the point is like kind of like above it, like there.
Okay, let's not worry about second scenario first. Do you understand what happened to the first scenario?
I think so.
Okay. So you agree with me, right? For the first scenario, when you do the top wire, where is the magnetic point going to be?
Under it.
It's going through the paper, right?
I guess.
Or you can say it's pointing downward.
My fingertips, right? It's pointing
Yeah.
down. Okay. Yeah, I see the bottom's pointing downwards too. But for number 2, the bottom, my right hand is pointing the same way from the top and the bottom.
No, for that relative position, right? If you are doing something above the wire, yes, it's coming out of the paper. But if that particular point is below the wire, it's actually into the paper. Do you see that?
Yeah.
So you have to imagine another point that's perpendicular, or say symmetric position, but it's above the top wire. Where did that point is going to go? That would be out of the paper. Do you see that? For the second scenario, right? You have a P point in the middle. Okay?
Okay, so
let's draw another point called Q point. Where is Q? Q is above the top wire. Symmetric position, right? Same radius. Does that make sense?
Is it like stacked, like up vertically, or is it placed horizontally?
Vertically on top of wire 1, on top of the top wire.
So this is going upwards. So it goes bottom wire, point, bottom wire, top wire, point.
Point Q, right?
Yeah.
I'm going to draw another Q, point Q, above the top wire.
Okay.
Okay, so I'm asking you, what is the magnetic force on P? What's the direction? It's going to be downward, right? What about on the point Q?
Like 0.
It's going to be upward.
For the top wire.
for the point Q, right? We're talking about another point, not P.
Wait, you said what is point P? I thought it was 0 because the bottom and the top cancel it out.
No, if we talk about point Q, we only talk about, say, well, here's the thing. When you do the second scenario, are you doing the top wire or are you doing the bottom wire?
I don't know.
Well, you got to do both, right?
Yeah.
You got to do both to figure it out. So what is the direction of the magnetic field when you do the top wire at P?
Into the paper, but I
Into the paper. Okay, you said it, right? I didn't force your word, right? You said
don't
into the
really
paper.
see why though.
Now you take a look at the bottom wire. When you do your right hand rule, your current is your thumb. Where are your fingers pointing towards at P?
It's like I can't really curve my fingers like that, right? Can't curve them the other way. So
Why not? It's still going that way. Right hand rule, right?
yeah, it's going this way, but it's the same thing. Are we talking about 2 or 1?
We're talking about scenario number 2.
Scenario number 2. Right hand rule says that thumb points in the current, and then whatever way that your fingers are curved is the direction of the magnetic field, right?
Right.
So on the top one, the top wire,
Yeah.
my thumb points this way and my fingers curve this way. On the bottom,
No. Don't say your finger points this way. That's hard to understand.
okay,
Tell me, your
Yeah.
finger is pointing into the paper or out of the paper? Top wire.
yeah, okay. I was talking about my thumb. My thumb.
The thumb is the current, right?
Yeah, the current points this way, and my fingers curve down, and they point into the paper.
So into the paper,
Into the paper, sure.
right?
And then on the
So
bottom,
at point 2,
I point
caused by top wire, into the paper,
Yeah.
right?
And then
Okay.
Yeah.
On the bottom,
the
same
bottom,
thing.
Same
You
thing.
point the current to the right.
Yeah.
Where your finger pointed at the P point, where is it gonna go? It has to come out of the paper, right? Because it's the same right hand rule. The only difference is, you said, why the change? Well, it's the P point is different. For that point P, relative to top curve, not the top wire, where is that P point? It's below that wire. When you talk about the bottom wire, where is that P point? It's above the wire.
Okay.
Therefore, their direction is opposite. Your
Okay.
P direction, your P position is opposite comparing to wire 1 and wire 2. Therefore, the magnetic force is going to be opposite.
Okay. How about for scenario 3? If the right hand rule states that, so it goes into the paper for the x-axis.
Scenario, right? Again, right? If you use right hand rule for P, the horizontal one is into the paper.
Uh-huh.
If you use right hand rule, the vertical one is into the paper. So they don't cancel. They reinforce each other.
So when you say into the paper, does that just mean towards the point?
Towards the point. Yeah, you can say that.
Okay, yeah, because I was getting confused. I'll just think of it as wherever it curves relative to the point. If it curves towards the point, it'll be into the paper. If it curves away, it'll be...
That's cool. Yeah, that's fine. Yeah.
Okay.
Away from the point, then that means into you, out of the paper.
Okay. All right, then I got it.
Okay. All right. I'll see you Thursday then.
Thank you.
Okay, you're welcome. Have a good one.
Yeah, you too. Bye.
Okay, bye-bye.